Welcome everyone to the 6th module of our Security Fundamentals series. We're going to have a look at secure cloud network design and some other stuff as well. Now for those of you who have just discovered this, welcome. And for those of you who are returning, welcome back. Now for the new guys and gals, there's a whole series here. So check it out. There's a playlist. Also, you'll be able to keep following along with the rest of the stuff. Now, let's get into our first section, cloud infrastructure. Now, considering this is meant to be a fundamentals course, I don't want to make too much assumption on your knowledge of cloud computing. So, let's get the deployment models dealt with first. And one of our first choices is a public cloud, which is usually what we use to describe most common cloud examples, where we are paying a cloud service provider like Microsoft, Amazon, Google, Hetzner, DigitalOcean, etc. to host our services and data. Now, usually with public cloud, this is a multi-tenancy architecture, meaning that you share that infrastructure with other customers. And I don't mean just in general. You might be one of many customers on that one server in that cloud provider's data center. So that you do need to be very careful about, because obviously shared infrastructure means shared risk. You don't know what those other customers are doing. And if anything goes wrong with how the cloud service provider is isolating you from those other customers, you could be in for a pretty bad time. Thankfully, though, we have got alternatives to this. You could go with a hosted private solution. I prefer calling this a public single tenant solution, where you can pay a cloud service provider a little bit extra, or it might be a lot extra, it all depends on exactly what you need, to be the only customer on that infrastructure, on that equipment. Now, this does help alleviate some of the concerns about sharing the infrastructure with other customers. However, you are still using somebody else's infrastructure and your data will still be traveling across the internet. So those risks need to be considered and thought out for you and your organization. If you are wanting cloud, but you really want to stay in control of everything, you could go private cloud, where you run everything yourself. Now with private cloud, the benefit is you become your own cloud service provider. The drawback, you become your own cloud service provider. You've got to worry about all the equipment, the hardware costs, all of that stuff. Ultimately, you don't really get rid of the costs of running a traditional data center, but you do get some benefits in terms of how you present the resources of the data center to the end users. You'll have the ability to more accurately tie the costs of various services to the users and the departments, which can be beneficial. Or you could look at a community cloud. Now, the community cloud, you and a couple of other organizations are working together to host your own cloud. Now, the benefit of this would be you and those other organizations are probably going to be in a similar industry, probably in the same country, and that would be beneficial to all of you, as that means that you could make sure you are legally compliant with regards to security and privacy and all that good stuff, while still sharing the costs of running a cloud environment. So that could be beneficial. But realistically, any organization I have seen that is of significant size and has adopted cloud computing has gone for this model, hybrid, where it's a mishmash of the above deployment models. Now with hybrid, you can pick and choose. I want public for maybe my office productivity stuff. I would like hosted private maybe for my customer relationship management system. I might want fully private for my database stuff. And that way you can still have cloud computing across the board using different deployment models that will meet your security and privacy obligations. So that can be pretty freaking cool. Moving along, we also have the cloud service models. And this is something else we have to watch out for when it comes to our security. First up, we have infrastructure as a service, platform as a service, and software as a service. These three are what I like to consider the original three, and we often like to represent them here as a pyramid, where you will probably have the apex at the top, and at the bottom you've got infrastructure as a service, platform as a service, and the top gets software as a service. Now, I personally like the pyramid this way because with infrastructure as a service, there's a lot of work for you still, but the costs aren't too bad. Think of it like building a pyramid. You've got a lot of bricks or whatever it is you're building the pyramid out of to place at the bottom, but it's not going to cost you a lot to get that building material up because it's still quite close to the ground. When you start trending upwards towards platform and software as a service, then you're going to be elevating that building material quite a lot and incurring a greater cost or building expense, but you don't need to elevate nearly as much. So let's go through the actual what you're getting versus what you're paying for. So with infrastructure as a service, you are basically paying the cloud service provider to run the hardware. You're using their servers, you're using their network, you're using their power, and in return, you can do what you like on their stuff, within reason, obviously. But you take those resources and divvy them up into VMs, which we'll talk a bit about just now. You install whatever operating system you want to put there, but the licensing and the cost of that operating system, that's your baby. And also any setup and integration, your baby. What services you're going to run on them, what platforms you're going to host, that's your baby. And obviously, whatever software, data, and applications you want to have, as well as users, are going to be all your responsibility. Basically, all you've gotten rid of with infrastructure as a service is the actual physical costs of running a data center. From a software perspective, everything is still your problem. But if you step up towards platform as a service, that is where the cloud service provider starts doing a little bit more of the software side of things for you. There, you'll probably be deploying pre-built templates or pre-formatted VMs with an operating system already sorted out. Don't worry about the licensing. The cloud service provider has sorted that all out and it's built into the bill at the end of the month that you're going to be paying. It's up to you to place the applications, the data, probably a bit of the integration into your existing environment. You get the idea. It's not too bad though. Then, if you step up to software as a service, the cloud service provider runs everything up to the application, and it's up to you to worry about the access, the data, the users, any policies, stuff like that. That's not too bad. So as you can see, the further up you go, the less you have to do, but the more you're going to be paying for it. It's very difficult to try and compare dollar by dollar what you're paying for software as a service and infrastructure as a service in relation to what you're getting. Obviously, because you're not comparing apples with apples, you're comparing apples and bananas here. But you can still draw the conclusion that you are going to pay less for infrastructure as a service because you as the consumer are going to be doing more. Obviously, I am assuming a public cloud service model here. Now, one of the big problems we have with modern cloud, and especially when it comes to the security, is that these three service models don't cut it anymore. We've got new ones. We've got things like database as a service. Now, the thing is, with a database as a service, is it just the database, or is it the middleware and the services across the network? Is it the front-end application as well? What's involved with that particular offering from a cloud provider? I don't know, because it varies from provider to provider. I've also seen things like communications as a service, where your email, instant messaging, VoIP, you name it, for communicating, can become a singular integrated cloud service. I've seen things like network as a service, and I absolutely hate that name because a lot of people sit there when they're new to cloud and think, how can my network become a service when I kind of need it to get to the cloud? Well, that's because it should be called network monitoring as a service, which makes way more sense. Basically, a cloud-hosted network operations center system would probably be the best way to describe it, and that's why I wish they would call it NMAAS, but sadly, I cannot change the way the industry works, I'm afraid. But what I can be grateful for from the industry when it comes to cloud computing is XAAS. The Cloud Council, yes, there is such an organization. I would like to think that sits at the top of the mountain above the clouds. I got a weird imagination, sorry. But the Cloud Council decided that with all these new service models popping up, let's just call it anything as a service, or XAAS, X being a placeholder like in algebra. Sorry for those traumatic memories I just brought back. Now, the great thing about this is it kind of deals with the future of cloud, where somebody could take an existing IT service and find a way to deliver it through the cloud, or come up with a whole new IT service and from day one begin delivering it as a cloud service. So that covers all the bases of future cloud products. Now, why do we recap these basics? Well, because it all boils down to this one key thing, the responsibility matrix. So what is the responsibility matrix for us? It's a table checklist. And what the purpose of it is to track who is responsible for what. Now, who's the who? Cloud service provider is one of the who's. Then the cloud consumer. And also both. What do you mean both? Well, there are going to be some things where you and the cloud provider will be co-responsible for something security related. And then obviously the individual items are the what. Like, for example, data security, backups, key management, stuff like that. Those are the kinds of things you want to check. Now, this checklist may be available from the cloud service provider, or you may need to create it yourself as the consumer by running through the terms and conditions, the terms of service, basically any agreement you might have with a cloud service provider. And that will allow you to figure out, okay, cool, this is what the cloud service provider is looking after. Great stuff. This is what I, as a consumer, need to look after. And that level of certainty, believe you me, is amazingly beneficial. Now, let's move on and talk about the cloud service provider's absolute responsibilities. Now, what I mean by absolute responsibilities is generally these responsibilities are across the board expected to be done by the CSP. Now, when I say across the board, I mean like from infrastructure as a service upwards, you'll find that they're normally responsible for these kinds of things. And the first and most obvious one would be the physical infrastructure and the security of the physical data center or the site where the stuff is happening. The cloud service provider has to handle that. I can't go there and sort out any physical security issues. I mean, even if I did get there, they probably wouldn't let me in. And I don't blame them. Then, when we talk about physical infrastructure security, we are talking about the computational security, so like processing, RAM, stuff like that. We're also talking about the storage security and obviously the network security. Speaking of network security, the cloud service provider will have to make sure that various customer traffic is kept separated from one another. The last thing we need is another tenant's data arriving on our stuff or vice versa. We also need to make sure that the cloud service provider is able to protect all their tenants from common threats like DDoS and stuff like that. Also, you might have attackers that just want to get into the cloud provider's environment and just see what they can do from there on. So the cloud provider needs to take their network security very, very seriously, as well as their storage of their backups and recovery data. The cloud service provider is to some extent going to be responsible for storing backups and doing recovery. However, that's one of the things where I would choose to make that a co-responsibility regardless of what the cloud service provider says. When I used to personally use a public cloud service provider, I still kept local backups of all my data, just out of paranoia. And although I never needed to rely upon it, it did help me sleep better at night. Now that I run my own private cloud solution for myself and my family members, obviously as the cloud service provider, I am responsible for the backups and all that stuff. And believe you me, I am following the 3-2-1 rule of backups. But also, we would like to know what's the cloud provider's strategy when it comes to recovery. And if I was a potential customer of a cloud provider, I would like to ask them, listen, do you have priorities when it comes to recovery? Do you recover certain customers before others, even if we're all at the same performance tier? Because I can guarantee you there is going to be a difference in priority. Then, very important, tenant isolation. This is literally what the cloud provider has to be able to do to effectively and cost efficiently operate a cloud. They need to be able to keep one customer's operations and data separate from another's. If they can't do that, it's going to become very difficult to run a cloud operation profitably. So they will probably be using virtualization and some pretty good controls as well, in addition to the virtualization, to keep stuff isolated. Now, we're going to get into the virtualization just now, I promise. But for now, let's carry on. With identification and access controls for tenant resources. Now, the idea here is that the cloud service provider will be doing a little bit of identity and access control so that when customer A wants to access their virtual server, customer A accesses their virtual server, not someone else's. That's what we're talking about here, that they can identify the tenant's resources and apply effective access control to it. Then after that, we have monitoring and incident response when it comes to their infrastructure and services that facilitates the tenant's operations. Please be aware, this does not mean the cloud service provider is responsible for all monitoring and incident response processes, just of their infrastructure and the services that facilitate what we are doing. So we are going to have some responsibilities here. And also managing the security and services between the data centers in different geographic zones. Because when it comes to stuff in different geographic zones, that probably means we're going to be using some sort of public infrastructure to get traffic from, let's say, a data center in Europe to a data center in the United States. So yeah, that needs to be done properly. But don't worry, it's not all down to the cloud provider. The consumer also has some responsibilities. And again, even if we're going with something like software as a service where we're responsible for very little as the consumer, guess what? There's still some stuff that we have to deal with. Like, we have to make sure that we are dealing with how do our users go through identity and access management. We need to manage that. The cloud provider doesn't know who works there. The cloud provider doesn't know what they're meant to access. You do though, so you've got to manage that still. Also, configuring the location for the services and storage. The cloud service provider doesn't know which region and which data center you want the stuff to be hosted in. Maybe you want it to be in a region with very good availability metrics. Great. But that region could be very far away from you, incurring greater latency. Maybe you would rather have lower latency. Well, the cloud provider doesn't know what it is you want. So they are going to expect you to make those choices. And every choice you make obviously has an impact with the security, the availability, the latency. You get the idea. Then we also have to worry about the user access control of cloud resources. How do we make sure that the users are accessing the correct resources and not some other user's resources? Now, this is not me repeating the IAM stuff. We implement the identity and access management solution. But we also need to make sure that we are carefully managing that if Bob has a cloud resource, Sally doesn't magically get to access it just because she's in the same department as Bob. That could be very bad for the overall security of the organization. We also need to make sure that we are keeping a close eye on our data security. The cloud service provider, again, does not know whether this data is public, whether it's private data, whether it's sensitive or confidential, or whether it's restricted. We have to do that data classification and apply the appropriate settings and tags to it. You never know, maybe the cloud provider is able to do the data security for you once you have properly tagged it. So we got that going for us. After that, we also have application security configuration. At the very least, you're going software as a service. And again, there's settings and features within any software as a service application that you can use to control your security. Fantastic. Then you have operating system security when relevant. When relevant? Look, if you're doing software as a service, you're not going to be worrying about the underlying operating system. But if you're doing platform as a service, I have seen some cloud service providers give you quite a lot of control and access to the operating system. It's just a pre-built machine. After that, it's up to you to customize. And then I've seen some where you don't touch the OS. You see it, but you don't work with it. So it varies. So obviously look at the particular product offering that you are interested in and determine where that fits. Cryptography is also to an extent the customer's responsibility, depending on the exact offering. It might be as simple a choice as, yes, cloud service provider, I would like you to encrypt data for me. But preferably, I would like you to control the cryptography. because that way at least you retain control of your data. If the cloud provider does the encryption, they can also do the decryption. Whereas if you're doing it before it arrives at their environment, they can't look at your data, which is obviously a good idea. Now, when it comes to cryptography, there are a few key responsibilities that the consumer wants to be absolutely sure is covered. Even if the cloud provider is doing the cryptography, you want to make sure that you've got a backup of the keys, especially the decryption key. Please, please, please keep that backed up. And also managing key security. That ultimately is going to be part of your responsibility no matter how the cloud provider offers you cryptography. But regardless, these bullet points are just expected absolutes. In your circumstance, when you and your organization are looking at adopting a cloud solution for something, you want to work your way through every security concern, every security possibility, every security control you could think of, and work out, is it the cloud provider who's responsible for this? Is it me, the consumer? Or is it both of us who are co-responsible? Double check for yourself. Now, let's talk about centralized versus decentralized cloud computing. Bit of an evolution in cloud computing because now we've got two interesting approaches to it. So let's compare them one by one. So with centralized cloud computing, there is one place where all your processing and your storage and all your cloud operations is taking place. Versus decentralized, this can be spread across multiple different sites, or even regions, or even both. Why not? Now, having a single location for processing and storage will probably minimize the latency experienced when opening some data and working with it. Downside, though, is obviously in that one location. If that one location is not there, oh dear. But we also have one location where all of the authentication is taking place when it comes to the cloud operations. Whereas with decentralized, authentication can be spread out too between different locations. Now, as I said already, with centralized, you do get a bonus in performance. With decentralized, there is a potential performance impact. Obviously, because everything's been spread out, there can be delays in getting communication between different sites and different regions and both. But it can be carefully managed to mitigate this. A good cloud service provider with a consumer who thinks it out carefully can get a deployment in such a way that decentralized will have capacity and performance put in place to balance out the delays and latency incurred through the decentralization. However, it is easier to get good performance with centralized options, both for the provider and for the consumer. So in general, with all things being equal, yes, centralized will be better performance because you're not having to put in extra effort. But that doesn't mean decentralized can't be high performing. It just does require a bit more effort. There's always a trade-off. However, your centralized options do trend towards a single point of failure. Let's say, for instance, that there is only one intercontinental fiber optic cable connecting that cloud provider to the rest of the world, and that cable goes down. Single point of failure. Let's say something terrible happens in the country where that data center is. It could definitely impact the cloud provider's operations. Single point of failure. Whereas the decentralized option, where your operations are spread out amongst multiple sites and multiple regions, you are less likely to have a single point of failure, at least on the cloud service provider's side. Now, besides decentralized cloud computing, the whole idea of decentralized networking, data sharing, computing, etc. has been around for ages. Blockchain that we mentioned in a previous video, that's decentralized peer-to-peer file sharing, torrenting basically. That is decentralized, where you can get your Linux ISOs, one of the legal uses for peer-to-peer file sharing. Content delivery networks, used to improve performance for various organizations like streaming services. IoT can also be a form of decentralized networking. Distributed data centers in a traditional organization where some of your data center operations are hosted at site A, some of your data center operations are hosted at site B. That's decentralized. And also the onion ring, which is used for anonymizing internet traffic for various reasons. Now let's talk about replication. With replication, what we're doing is we are duplicating the active data that we rely on across our infrastructure. Now, the thing about replication is it is intentional, okay? When you got duplicates that you didn't plan on having because somebody copied the same thing to another place, for example, that is called duplication. Replication is intentional duplication to improve availability. Plain and simple. It can also help improve performance as well, because you could replicate the data closer to where the users are. For instance, if you got users maybe in the Far East, you could ensure that some key data they work with regularly gets replicated to a site in that region. If you've got a lot of users in Africa that access particular data, you could replicate to a data center somewhere in Africa. You get the idea. You can get very crafty and clever with this. Now, when you do your replication, you could do local replication within the site or within the region. Generally, with local replication, it is within the region, maybe not within the site though. But a good idea is also to make sure you've got regional replication as well to cater for geographic discrepancies. And trust me, keeping data closer to people helps. For those of you living outside of the United States, you've probably experienced this, where an advert on YouTube will load quicker and in higher quality than the video you intended to watch. And this is because with YouTube's advertising, they normally have adverts in the region that are relevant to that region, because I don't want to see toothpaste or beer or whatever adverts. In case you're wondering, that's the last two adverts I've seen that are for products you can't get where you live. So that server is closer to you. It's in your region. And then the video you're probably wanting to watch, like this one, is probably being stored in North America until it gets popular enough to get replicated into other regions. So yeah, it happens all the time, even on this platform right now. But another good idea for our replication is to create geo-redundant storage, so that no matter what happens across the world in terms of geography and politics and all that fun stuff, we've got redundant copies of our data in the cloud environment, keeping our stuff, hopefully, safe. Now let's look at some technologies that underlie cloud computing, like virtualization. And here's the thing. Once you understand virtualization, you can start maybe looking at implementing your own private cloud. There's a whole bunch of cool things you could look at implementing to do this. So why virtualization here? Well, without virtualization, cloud computing wouldn't become the big thing it is right now. I stand under correction, but I'm sure I read somewhere that the concept of cloud computing was first put forward sometime during the 1970s. And the first service that could be thought of as cloud computing was from Salesforce back in the late 90s. But without virtualization, they would not be able to operate at the level they do with the economies of scale that they do without virtualization. Think of it this way. I could go and buy a Ferrari, or I can go and buy a bus. Both cost more or less the same kind of money, and try and use both vehicles to run a transport business to get people from point A to point B. Thing is though, I'll be able to get more people on the bus and therefore sell tickets to get people from point A to point B at a much lower price than I could with the Ferrari. As fun as it would be to arrive at point B in a Ferrari, the people who are interested in it would probably be more inclined to save a penny. So virtualization helps a lot, because I can run a load of things on the computer with unused resources. Now, to do virtualization, you need something called a hypervisor. And there are two main types of hypervisor. And the first one I want to introduce you to is the Type 2 hypervisor. Now, with the Type 2 hypervisor, you have your computer hardware, you have an operating system installed upon it that we're going to call the host operating system, as it's going to host the virtual machines and their guest operating systems within them. And then, on top of that host operating system, I'm going to install a software hypervisor alongside other applications that would be on my computer, like for instance my document processing tools, my web browser and stuff like that. My hypervisor is just that, an application that exists on my machine. Now, some examples of hypervisors you could get your hands on. If you're using Windows 8, 8.1, 10, or 11, Pro or Enterprise Edition, you get access to Microsoft's client, Hyper-V. If you want to maybe be a little bit more flexible, you could look at using VMware Player. The non-commercial edition is available for people to play with. And my personal favorite is Oracle's VirtualBox Manager. That's my personal favorite one, mainly because it works on every operating system and it does a very good job at virtualizing most operating systems you want to play around with. Now, what the software hypervisor is busy doing is it's asking for hardware resources from the host operating system, CPU, memory, storage, networking, etc. And it uses those to create virtual machines, basically virtual imitations of actual computers. So you'll get some virtual hardware upon which you can install a guest operating system. And it's good enough to trick any operating system into working on it. Now, some operating systems are virtualization aware and know that they're running on a virtual machine. I remember back when Microsoft brought along Windows Server 2012. Showing my age a little bit, I know. But that marked a point where Windows became very virtualization aware, as Microsoft went from a per instance billing model to a per CPU core billing model, because people were running Windows Server on a VM and just giving it a load of CPU cores. And they were paying for one instance. Whereas by billing per core, you were paying fairly. If you gave one VM running Windows Server loads of CPU cores, or one VM very few cores, but loads of those VMs, you were going to be paying the same as the other person. So worked out fair. And Microsoft got their pound of flesh from us. Cool. And then you can run whatever operating system you like, and you can run the applications within. And the nice thing is, the guest operating systems can be completely different from each other, and completely different to the host operating system. And this is great because you'd literally give the VM exactly what it needed to operate at the level you needed it to operate at. That's pretty cool. But I did say there were two types. So type 1. And I don't know why we write them in Roman numerals. It's just a thing. I'm just going with it for now until I find out why. If any of you guys do know why, comment down below. Enlighten me if you know. But with type 1, what happens is you got your hardware and then your hypervisor. Wait, what? So there are two ways to achieve this. You can either have a hardware hypervisor, where it's a box that gets plugged into the hardware, or it's a highly specialized operating system, which can run VMs, and that is it. Now, this takes away flexibility, but I'll give you the trade-offs now. And then on top of this, you run your VMs. Now, to me, this is pretty cool, because what you do get here is more resources available for the VMs, because you're not dedicating CPU and memory to a host operating system, which is pretty freaking awesome. And it also can be way more stable, because with type 2, your host operating system can have bugs and instabilities and security vulnerabilities that can lead to it and any applications, including the hypervisor, failing and taking down the VMs with it. Whereas your type 1 hypervisors are going to be a lot more reliable, as they're only doing one thing and one thing alone, running VMs. Now, it's not to say they wouldn't have their own bugs and vulnerabilities, but they're going to have far fewer of them, which is obviously good for us. The downside, though, is with type 1, that is all it can do. Run VMs, and that is it. Nothing else. Whereas type 2, you can do whatever you like with it. Now, on a personal level, I love using a type 2 hypervisor, because I can then run VMs, and once I'm done with those VMs, turn them off, and I've got a normal computer again. In fact, a couple of my videos have been done with VMs. See if you guys can go and figure out which ones I used a VM for, and comment down below, and I'll tell you eventually which ones were which. But it's wonderful because it does give me flexibility. Now, if you want to play around, if you want to experiment, if you want to learn, maybe you're a developer and you want to test your software in different operating systems, Type 2 is great. If you want to have virtual servers in a data center, Type 1 is great. And believe it or not, doing that in a data center can be very beneficial because you'll need fewer physical servers. You will also be utilizing your physical servers more efficiently because, fun fact, the difference in efficiency between a computer that is off and one that is idling versus one that is idling and one that's running under load is surprising. It is more efficient to run a computer at load than to have a computer idling and doing nothing but still drawing power just to remain on. So the Type 1, you actually do get some energy efficiency going there as well, which is pretty freaking awesome. But here's the thing though. If your goal for running virtual machines is so that you can run multiple applications that are not compatible with each other, or you are unable to run multiple separate instances of those applications and isolate them from one another, virtualization is actually kind of inefficient. Let's say you're trying to run two applications, application A and B, and they're mutually exclusive. If you have A, you can't have B because it'll give you problems. And if you have B, you can't have A because it'll give you problems. Well, you could run two VMs and stick each in a separate VM. Awesome. But if they're both using the same operating system, you're running that same OS 3 times at most. One per VM, then obviously maybe one as a host operating system. This is not an efficient way to get multiple applications working alongside each other that normally would give each other problems. That's why containerization was created. Now, containerization is probably most closely related to Type 2 virtualization because with containerization, there's going to be the hardware in the host OS. However, unlike virtualization, we don't have a hypervisor. We've got something called a container engine. A very, very popular container engine is Docker, but it's not the only one. Now, what happens with the container engine is the container engine creates an isolated environment in which we can run the binaries and the library files that an application might need, and then the application itself. The containers themselves, though, use the common host operating system. So this is where we get that efficiency gain. I'm not having multiples of the same operating system over and over again. However, the downside of containerization is if I've got an application that was developed for Windows and I'm trying to run it on something like Linux, bad news, that's not going to work for you. You have to go full virtualization there. But with anything that does run on Windows and you want to containerize it, go for it. Anything that runs on Linux and you want to containerize it on Linux, go for it. It'll work. And you can do this with more than just one application. You can have an application B here and multiple instances of it. So how would containerization fit into cloud computing? Well, as a software as a service provider, as long as I can keep every application instance separated and provide it to each customer, that could be a very efficient way to offer a software as a service solution. So both virtualization and containerization are pretty cool. And you can do these things in your home environment as well without much difficulty. As long as you've got a computer strong enough to do it, you can go crazy. Now, we've got some newer things that have been coming along with cloud computing, like, for instance, a virtual private cloud, or a VPC. Ooh, that sounds interesting. So what happens with VPCs is we're looking at having a secure, isolated cloud environment within a public cloud. Cloud within a cloud, basically. So essentially, we're getting a miniature cloud inside of the cloud provider's environment that is heavily isolated, giving us a lot more privacy without having to necessarily look at an expensive option like a hosted private solution. In fairness to security, it is not necessarily as good as a hosted private solution and definitely nowhere near as private and secure as a private cloud. It is a step in the right direction while keeping costs pretty reasonable. And you can use it normally as though it were a private cloud, but it does get hosted elsewhere. It's hosted on the cloud provider's infrastructure. So that's pretty cool. Now, I'm sure most of you guys are okay with that idea, but we've also got some pretty interesting things coming along, like serverless architecture. You heard me right. Serverless architecture. Now that sounds pretty interesting. So what happens here is your computing and storage resources are going to be used to create a pool of resources, and you are not going to have a specific operating system running on them. It's just a pool of computing resources. And what happens is your applications run on top of that pool of computing resources and get access to the compute and memory and storage and networking and whatnot that they need. No operating system there. And if you think about it for a moment, why not? I mean, we've virtualized the hardware, and all an application really needs is just access to the resources to process. Why do I need an operating system now? Why would I need to install Windows? Why would I need to install Linux? Why would I need to install Mac OS in the cloud? It would be more efficient for both me and the cloud provider if the application could run directly on the pool of resources I am leasing from the cloud provider. And that's the idea behind serverless architecture. Now, scarily enough, the idea of serverless architecture, even though it's quite new, has been taken a step further with microservices. Now, as I said, this is a step further, so it's an extension of serverless architecture. And what's happening here is our applications are going to be built as little services that you and I, as the customers, could pick and choose from. And then we can get them to interact with one another as we need them to as well. So as a customer, I might say, ooh, I want email and I want instant messaging, but I don't want VoIP and I don't want video conferencing. I can pick those smaller services and have them work together and not pick the ones I don't want, which means I don't pay for something I'm not going to use, which is freaking cool. And this also means that my billing becomes very, very flexible. And what's also nice for both me and the cloud provider is the customer builds are not exactly the same. Now, the reason why this is cool is it means it's a lot harder for hackers to create a profile of, okay, these people are using this particular thing from this cloud provider, which means they're all the same. No, they're not going to be the same anymore. So even if an attacker does succeed against customer A, the other customers are less likely to be affected. And the cloud provider is also going to be more secure for that as well. So it's pretty awesome. But it's not without risk, obviously. Customers might not choose every service they actually need and then have an unsatisfactory product. So microservice cloud offerings can be really awesome, but should definitely be treated as an iterative, constant, continual integration, continual development process of add to it, improve it, add to it, improve it. You get the idea. Now, when you are looking at cloud computing, there are considerations that you need to make. First and foremost, cost. Cloud computing does offer the advantage of pay as you go, pay for what you use, which is great. Now, after the cost, you also got the elasticity or the scalability benefit of the cloud. Now, when speaking about cloud on its own without bringing security in, we do like to use the term elasticity to describe cloud operations, because with cloud computing, you can grow or shrink your operations based on consumer demand. Now, that is what we refer to as elasticity. It's basically just being pedantic and wanting to make it sound better than scalability. Because scalability, by dictionary definition, means it is easy to grow the environment in a sustainable way. But traditional scalability does not allow you to shrink the environment in a sustainable way. Cloud computing does let you do it sustainably. So there is a valid argument to be made for calling it elasticity and not scalability. But ultimately, we do need to look at it. How easily can we grow our operations when we need to? How easily can we shrink our operations when we need to, based on demand? And you might say, well, how much of a concern is that? Well, let's say you want to make it very easy to grow your cloud operations when needed. And when a user identifies that things aren't keeping up, they could do something that automatically provisions more cloud resources for something. That sounds great. But if your user is able to do that unchecked, you could land up having loads of unnecessary cloud instances running, costing you more than you really need. And only when you realize, whoa, the cloud bill's gone way up this month, and you investigate, do you realize you need to now dial it back a bit and slow it down. So the elasticity and the easy growth, as great as it is, does come with some risks. Then, resiliency. How good is the cloud provider at standing up against various threats that would take down an organization running their own data center? How well does the cloud provider stand up against DDoS attacks? What about malware, ransomware specifically? What about natural disasters? What about service outages like ISPs going down and certain parts of the internet infrastructure like CCOM cables going down? Stuff like that could definitely have a big impact. So you want to look at what's the cloud provider's resiliency reputation like. Also, ease of deployment. How easy is it for you to get your stuff up and running in the cloud? Because if it's easy to deploy in the cloud, we could take this as an opportunity to improve how our stuff is deployed. Because I won't have to spend as much time getting stuff up and running. I can spend some of that time making it run better, more stably, more securely. And to me, that sounds like a big, big benefit. So looking at the user deployment can be beneficial to us, as it could free up some time and mental bandwidth to improve security. What about recovery? How easy is it for us to recover our operations in the cloud when something goes wrong on our side? How easy is it for the cloud provider to recover when something goes wrong on their side of the responsibility matrix? All of that needs to be looked at. And then, what about ease of migration? Wait, ease of migration? Yeah. What if you want to move to another cloud provider? Who says you want to stay with that cloud provider forever? This is not a monogamous marriage. You are not required to stick with that cloud service provider till the end of time. You want to be able to move from one provider to another. You want to avoid having what we call cloud service provider lock-in, where it's easy to get in, but it's difficult to leave them. You want to make sure that you keep your options open, because today, cloud service provider A might be the best for you. But you never know, maybe tomorrow, the metaphorical tomorrow, not literally tomorrow, cloud service provider B, it turns out to be a better value proposition for you. And you might want to be able to migrate to them easily. You want to try and make sure that you can migrate away from that cloud service provider. Believe you me, all of them make it easy to migrate to them, but leaving them, they always make sure there's as many friction points as possible when it comes to leaving them. Speaking of which, service level agreements and interoperability security agreements and interconnection security agreements, whichever term you prefer, should also be looked at. And please be aware that any agreement between you and a cloud provider can be negotiated. Don't write yourself off as, oh, I'm some small organization in some part of the world. Why would these big tech cloud providers negotiate with me? Easy. Because if they don't and one of their competitors do, who are you going to go with? The one that's likely to negotiate with you and give you some customized terms and conditions and service offerings. So never write yourself off. Then, power. What type of power requirements need to be met by the cloud provider? Are they in a region where electricity is stable, where it is cheap, where it is reliable? That all matters. Because if it is not cheap, if it is not reliable, if it is not widely available, that could lead to surprising and undesirable outages. And this can happen all over the world. I've actually seen stories of cloud service providers building their own power supply infrastructure to better guarantee power delivery to their data centers. And if that's what's been done with the cloud provider you're looking at, well, that should just give you a little bit more confidence that their data center is not going to suffer a power outage. Then, what type of compute resources do you need? And don't think it's going to be a one-for-one translation. You actually could probably get away with less processing, less memory, and maybe a little bit less storage when it comes to a migration from physical on-prem to hosted in the cloud. But work it out carefully. What do you need at any given point in time? And that's what you need from a computational resource perspective. Speaking of, other things that you would want to look at when it comes to what you have already versus what you're going to be moving will be your data protections. You want to make sure that your data security is going to be as good, if not better, once moved to the cloud. And also, a special bit of warning, some countries have data sovereignty requirements of businesses and companies and organizations operating within their borders. Now, data sovereignty means that that data generated within that country is not allowed to leave that country. Or if not necessarily not allowed to leave it, it's restricted in how it's allowed to leave and what uses it can be under. Now, if a country has data sovereignty requirements, it is the consumer's responsibility to ensure they're meeting the requirements and obligations, not the providers. I cannot expect the likes of Microsoft, Amazon, Google, etc. to keep track of every country's legislation and regulations when it comes to data protections. Speaking of, you also need to make sure that you are handling data protections that might apply in other countries as well. Like, for instance, GDPR. Even if you are not in Europe, if you host and process European citizen data, you are subject to some clauses within the GDPR requirements of the European Union. So that also kicks in as well. So definitely keep an eye out on data protections. Also, another important thing to look at is patching capabilities. What type of options do you get for updating in the cloud? And also, while we're at that, could automated patching taking place within the cloud possibly affect your operations? Because if you've built a particular application or service around how something currently works and it gets significantly updated, that thing might stop working. Can you roll back? Can't you roll back? Can the cloud provider help you here? Or they're not going to help you here? What's going to go on? You need to consider those kinds of things, especially if you've been building yourself around a particular setup and a particular version of any piece of software, whether it be an application or an operating system. Then, what type of communications are you going to have to the cloud service provider? Because obviously that's going to affect how you are going to make sure that your security between yourself and the provider is being handled. If you're going direct to the cloud service provider, or are you going through a cloud access security broker, or are you using Secure Access Service Edge or SASE, whatever. Those are different ways to get to the cloud provider. Direct, you're just going to them straight over the internet. Access security brokers, trusted third party. SASE options, this is where the cloud provider tries to have a node as close to you as possible so that they don't bring a third party in. All up to you. I am kind of partial to cloud access security brokers for a few reasons. First of all, I do believe in supporting businesses wherever I can, but that's beside the point. What I like about cloud access security brokers is they usually operate within the country, province, state, wherever it is you are, and are familiar with legal requirements, regulatory requirements, and organizational culture and regional culture. And it just makes life a little bit easier sometimes. Plus, they're probably going to be in the same time zone as you, which means support is going to be a little bit easier to get sorted out. But those are all some considerations that you have to think about when looking at your cloud architecture. And honestly, I could probably make even more here if I wanted to. But these are the big things that are going to have the biggest impact in terms of your security and your availability, as well as the benefits you will get from going to the cloud. Now, for embedded systems and other unusual network technologies, the other stuff I mentioned at the beginning of this. Just got crowbarred in here, sorry. I'm just going with what CompTIA has in their Security Plus here. Anyway, let's go into it. So first of all, what on earth is an embedded computer system? It is a specialized computer that gets built into ordinary everyday things. It's a little bit unusual for a computer to be built into. Now, with embedded computers, there are commercial, industrial, and consumer use cases for these things. Smart appliances are a common consumer example of an embedded system, where a computer gets built into a TV, a refrigerator, a washing machine, you name it. Your mobile devices, like your phones and your tablets, it's another embedded system. I mean, think about it. Cell phones became smartphones when we started embedding proper computing capabilities into them. In-car systems or in-car infotainment systems, whatever they're going by, doesn't matter. Industrial controls to manage things in factories and production plants and stuff like that. medical appliances, building automation, stuff like that. So that's the idea of an embedded computer system, where a computer is built into something that is not really a computer, but does benefit from being computer controlled or computer enabled. Now, in some cases, these embedded computers will be using real-time operating systems. Now, I want to take a little detour and just explain to you guys what on earth is a real-time operating system. Windows, isn't it? So with a real-time operating system, what you're looking at is an OS that can handle a large number of requests that usually come from an external source, like a sensor. And it's going to have to do processing in a short amount of time with a very precise deadline for the results of that processing and computation. So it's going to receive some data on its sensor, and within, let's say, 3 seconds, it's got to have an answer. 3.5 seconds? Sorry, too late. The world's blown up. Okay, maybe I'm exaggerating a little bit there, but it's got to be by a fixed deadline. Now, usually, the real-time operating systems will have minimal functionality beyond what they need to do, obviously, so that they're not going to be multitasking things that they don't need to. Oftentimes, they're going to require fairly powerful computers to run and get those deadlines met, or they're going to run on ASIC computers, application-specific integrated circuit chips, where they literally run the exact thing they need to do, and that is it. They're optimized for that one task and that one task alone. Anything else, they suck at doing. And this can lead to some great security and some very good stability when a real-time operating system is done right. My favorite example of a real-time operating system would be the types of things used by air traffic control systems. Because think about it. It's going to have to take data from radar and flight telemetry systems. It needs to calculate data to make sure 2 planes don't crash mid-air. It needs to help us bring those planes into land safely or take off safely. And it's all got to be done by a particular time. We can't have seconds going to waste here. We can't have minutes of the computer freezing on us. This is where real-time operating systems come into the equation. So they're absolutely fantastic. They're amazing. They're wonderful things. But you don't always need to use a real-time operating system, obviously. Like we said, smart TVs are embedded computers. And I don't think people are going to die if my TV plays up on me. Anyway, let's look at industrial control systems. Industrial control systems are definitely a situation where we'll be encountering embedded computer systems that have got some serious ramifications if their stability and security is affected. And please remember, the stability and availability of a system is as much to do with security as keeping out the hackers and the malware. Alright, so what do we have inside of an industrial control system? Well, to build an industrial control system, the following components are needed. You need a human-to-machine interface of some kind, some way for a human being to engage with the computer and either get information from it or plug information into it. This may be a terminal, this may be a highly customized output display with a keyboard or a series of buttons to press. It's going to be something that allows a human being to engage with the system. We're also going to have something called a data historian. Now, data historians are sort of like miniature databases, but for industrial control systems. We're not going to be using SQL and stuff like that here. It'll be like raw text dumps into a corpus of data, or it might be a CSV file or something like that. But basically, it's going to be a place where data gets stored long-term for an industrial control systems engineer to come on and have a look at and review and stuff like that. And usually the industrial control systems themselves, the heavy machinery and stuff like that, will be managed by something called a programmable logic controller, or a PLC. It looks like a giant circuit breaker with a network cable plugged into it. But it is a miniature computer that follows a very, very straightforward programming language, usually a language that is relevant to the vendor who makes the PLC. They're very robust. They're highly reliable. They don't mind being stuck in some of the worst environments possible from a temperature, dirt, humidity perspective that would normally destroy other computers. They're normally very, very good. They're not cheap either, though, but they're great at what they're intended for. And there might be a SCADA system or a supervisory control and data acquisitions system. Now, SCADA systems and ICSs are closely related, but here's where one of the differences comes in. If I was operating a load of different sites, industrial sites, factories, mines, refineries, things like that, each of those sites can have an industrial control system. The SCADA system will allow us to monitor all of those industrial control systems, maybe from a centralized location, and control them. So think of it as like a centralized coordination system for industrial control systems. That's probably the best way to describe SCADA. Now, in terms of where do these industrial control systems get used, well, I've kind of been alluding to them already. Energy production, whether it be fossil fuels, renewables, nuclear, whatever. Industrial control systems can be very widely used in the energy production space. Also, any industrial processing like mining, oil, agriculture, etc. Can also get used in manufacturing, like with factories and stuff like that. Can be used for transit systems, to coordinate traffic lights, to name but a few. The industrial control systems will pop up all over the place. But something that's getting a lot more popularity nowadays is IoT, or the Internet of Things. Now, the Internet of Things is where ordinary stuff is getting a microcontroller or a microcomputer with sensors and connectivity, keyword connectivity, built into it. Now, usually that connectivity is wireless in some way or form. And the idea of IoT is that we can have these arbitrary things like light switches, wall sockets, specialized sensors and IoT products in the room, monitoring and even controlling certain things. A very useful example would be for energy efficiency. The IoT systems could check, okay, somebody's just walked into the bathroom. Okay, let's turn the lights on. Let's make sure the air extractors are turned up a notch, stuff like that. IoT could also be pretty useful as well for safety. In the event of a building needing to be evacuated, IoT sensors could keep track of how many people have entered the building, how many people exited the building, and help us figure out, somebody's still in the building. That could be very useful for emergency personnel to know when responding to maybe a bomb or a fire or something horrible like that. So these things do have cool uses. But a very popular thing that IoT does that is unique is often it does have some sort of cloud integration option available to us to make it easy to monitor, connect, and communicate and control an IoT product. Now, another key thing as well with IoT, it's different to things like industrial control systems, is that the common connection methods are pretty normal actually in the computer space. With industrial control systems, you actually have very specialized connections and very specialized protocols and services used to network and communicate. But with IoT, you're looking at things like ordinary Wi-Fi. Yep, seriously, that same thing that your phone and your laptop uses. Maybe Bluetooth, or realistically, BTLE, Bluetooth Low Energy. Normal Bluetooth standard, but way more energy efficient. Zigbee, Z-Wave, and ANT+. Okay, in fairness, those last three are a little bit IoT specific, but more available and more likely to be encountered in your day-to-day life than something like S7 comms, which is a very vendor proprietary communication standard for a PLC for the industrial control systems. So, cool. Now moving along, what makes IoT interesting and concerning for security is this. IoT devices often have very limited processing and memory capabilities, which means it is very difficult for us to implement strong security solutions, and also limits our ability to implement good cryptography on network communications. So IoT devices generally don't have the greatest internal security and also don't have very good cryptographic processes protecting the communications going over the network connections. And this can be a big issue, especially if you're dealing with Wi-Fi. Then you got this challenge of a well-developed product versus cheap, low-quality products. You will come across a smart plug for the wall, lets you control the appliance, turn it on, turn it off, stuff like that. And as a consumer, you'll come across this very expensive one from a reputable vendor, and then you'll come across this really cheap one. Never heard of the vendor before. Probably never will either. What's the average person going to go for? Well, they're going to go, they look like they do the same thing. I'm going to go with a cheaper one. Now, the thing is that cheaper one might be less reliable. That cheaper one probably will be less secure. You're trading off a lot to save a few bucks here, which is not always the great idea. The well-developed one might be more reliable, might give you a guarantee, might work for years and years and years before giving you any problems. So you've got to think about this very carefully. Do you go for the good one or do you go for the cheap one? Now, I'm not saying paying lots of money always means you get something good. Please don't take it that way. But don't straight away choose the cheap one just because it's cheap. And don't always assume that just because you're paying a lot of money, you're getting a good product here. You know what you want to do? Research. I can guarantee you somebody else has already bought that product. Go see what they think about it. And don't trust the reviews on the website that you're going to buy the thing from. That can be curated. Rather go someplace that's a little bit more neutral, like Reddit, for example, where you're less likely to have a corporate interest shutting down a certain narrative or comment being made. Now, another challenge we have with IoT, very little standardization is happening in the IoT space. There are efforts right now underway to try and standardize IoT and make it more reliable, more secure, more predictable, all that good stuff. But we're nowhere near a point where there's a good standard that is widely utilized and implemented for IoT products. And these devices may collect and transmit sensitive information. And don't take the vendor's word on what their device does. There's been a history, both recently and long term, where a vendor says, oh no, all this data is kept and processed locally on the device. It is never sent to any of our servers. And they were proven to be lying. So don't take a vendor's word on whether the device is collecting data or transmitting or not transmitting it securely, whatever. Rather do a bit of research, do a bit of investigation. And if you're doing this for the workplace, buy one of the thing and test it. Whatever way you can, test it. If you need to use something like Wireshark and do a traffic capture, do so. That way you know what you're getting yourself and your organization into. On a personal level, very, very difficult to justify the testing thing, because when you unbox the thing, you might not be able to return it. But that's where the internet becomes a useful thing. Bit of research, and don't be an early adopter. Let somebody else pay the price of being an early adopter. But what I can do is give you a couple best practices when it comes to implementing IoT. So first and foremost in the workplace, track and manage these devices. You should already have an asset inventory of some kind, but you might want to make a dedicated one for IoT appliances. It would be a very good idea to do this. Then, patch and remediate these devices wherever possible. Ideally, it would be worth us considering that the vendor has a good reputation when it comes to releasing updates and supporting their products. Maybe it's a good reason to spend a bit extra to get a product from a well-reputed brand or vendor who, if there is an issue, is likely to release an update that will fix the issue or at least improve the situation significantly. Definitely change the default password, please. These IoT devices will come with a default set of passwords or credentials or anything like that to give you some level of security. But it's very easy to overlook and forget to change these default credentials, especially when the implementation of that IoT product can be challenging already. You spend so much time getting it working that you don't want to mess with anything now that it's working. Well, bad news for you. That is the exact mindset that the bad actors out there want you to go with. Cool, it's working. Can I make it work securely now? And if doing so makes it not work, all right, your new challenge. Okay, it's secure. Can I get it working and keep it secure? You have to get both. It needs to work and it needs to work securely. You can't have one or the other. They mustn't be mutually exclusive. It must be able to work and it must be able to work securely, not just working only. Then, What protocols is it running? What services is it using? If you can, implement it in an isolated network and use Wireshark and some sort of network tap to allow you to intercept the traffic and see what is being sent. Ideally, you want to see encrypted protocols, not plain text protocols. And even if the protocol is proprietary, cool. Homework. Is that proprietary protocol encrypted or not? You want to check that kind of thing. Then, understand your IoT endpoints and what they're being used for. This will help you think carefully, because you don't want to use low security devices for critical and dangerous things. For instance, an IoT plug should not necessarily be used on somebody's oxygen generator if they're on oxygen support, for instance. If it's an unreliable motion sensor, should probably not be used for a security system, for physical premises security. You get the idea. Understand the IoT endpoint's purpose and what its capabilities are. And if it's got a significant, important thing that it needs to do, but it's not reliable, it's not secure, maybe not a good idea to use it in that particular role. And if you can, segment your network. Isolate the IoT appliances on their own separate LAN or wireless LAN, Wi-Fi, so that you can have a security gateway like a firewall or a UTM or a next generation firewall, keeping that particular network segment secure from the rest of the network and vice versa. It's a very good idea. Okay, now moving along to another topic that we want to talk about, the perimeter model. Now, I did briefly touch on the perimeter model and zero trust security in a previous video, but now we're going to smash it out properly. So the idea of the perimeter model is a bit of an old one. Still worth understanding, but also understanding its limitations. And the idea is the organization has a boundary, a perimeter. Inside of this perimeter, we will have our servers. Inside of this perimeter, we will have our end users. And as long as it is a device within the perimeter, it is trusted. We can assume it is safe, it is secure, because, of course, we're not going to implement something that we don't think is safe and secure. Okay, cool. And then we can implement a gateway at the perimeter to other infrastructure like the public internet. And what we do is we treat everything outside of the perimeter as untrusted. Sounds like a good idea, right? The problem is, though, the perimeter is failing us. Deperimeterization has been going on for a while now. Now, with deperimeterization, what we're looking at here is a breakdown of the traditional boundary of what is and what is not trusted. And the things that are causing this are technologies that allow for stuff to exist outside of our environment that should be trusted, and for things to come into our environment or our perimeter that shouldn't be trusted. Things like cloud computing. Our operations, our data now exists outside of our environment. Okay? Remote work. We should be able to trust the user's computer, right? But now it's at their home. I don't know what's on their network. I don't know if maybe their device has been compromised because maybe little Timmy or little Susie has been playing a game on the web browser on their computer. I don't know what's been happening. Mobile devices. These are devices that can come and go and very easily bring threats into our environment. We're also outsourcing, bringing in contractors, bringing in consultants, far more than we ever did. Now we've got people outside of our organization, outside of our perimeter, outside of our trust environment, basically, that have access to our internal resources. We're using wireless way more than we ever have before, which makes it a lot easier for rogue devices to get onto our network, especially if network access control and network monitoring and asset tracking is not being properly done. And then this gets 10 times worse when you allow people to BYOD or bring their own device, where they get to use their own personal phone, tablet, laptop, whatever, for work purposes. That device could be bringing in any number of threats. So the perimeter is failing us. We have to go with another model. And that other model is zero trust. Now, the idea of zero trust is all entities, whether it be a user, a device, a service, whatever, is not trusted. Even if it is inside the traditional perimeter, we do not immediately trust it. Okay? So, doesn't matter whether you're inside or outside, you are not trusted. Simple as that. Now, you might think, well, then how are we going to work? How are we going to do stuff? Easy. Trust will only occur once an entity has been validated. So, for example, if you're a user, you are not trusted until you've authenticated. Oh, okay, cool, that makes sense. What about a device, though? Well, if the device doesn't appear in the asset inventory, it's not trusted. What if it's a server? Certificates. What about services? IAM and access control will cover the services at some point. So there is always a way to validate these entities. Okay. Now, another thing about zero trust is it's not a once-off validation, hey? You must redo it regularly. I mean, think about it. I don't trust Bob just because he signed in on his first day at the job. I make Bob authenticate every flippin' day he comes into the workplace. Zero trust, we go with the whole idea of it could be compromised, it could have been affected since I last looked at it, let's validate. Yes, it does add a bit of a delay, but this is what modern security is about now. We can't have all these fun things like cloud, mobility, BYOD, and work from home if we don't start making these things secure, in addition to being convenient. So, what gets involved? What are the components that make up a zero trust environment? Well, first of all, good networking and endpoint security needs to be implemented. Things like detecting a new device, validating whether it's known or not. If it's known, okay, cool. Is it a good known? Is it a bad known? Stuff like that. If it's not known before, okay, let's find out who does this device belong to, stuff like that. Then, threat detection. With good threat detection, we'll be able to pick up on various attack techniques and look at what's going on in our environment, and if that activity in our environment exhibits the characteristics of that threat signature, well, we don't trust it. We rather require an administrator to review and then approve it. We implement good identity and access management solutions. We implement proper, strong data protection, and you don't get access to data until you have properly authenticated and been authorized and all that good stuff. We also ensure that policy enforcements are taking place. If I've got a policy that prohibits remote workers accessing certain files due to their sensitivity, but they can access it when they're at the office, so be it. That's a policy that we must enforce, and we minimize on exceptions to the policy. There will always obviously be exceptions, but we minimize them so that we're giving as few gaps that attackers can take advantage of as possible. We also do as much network segmentation as possible. The absolute zero trust enthusiasts, if given the chance, they would have a network segment with one end user and one server in it. Only one host basically per network segment, which, yeah, I suppose from a purely security view would definitely make sense, but from a realistic perspective, no, you can't segment that much. Still not a bad idea to start thinking like that, though. And doing as much for cloud security as possible, because cloud integration is one of the big things that has led to deperimeterization and the need to implement zero trust. And then network visibility, comprehensive and continuous monitoring of your network. So you might think, hang on, but none of this is like revolutionarily new or special or anything like that. No, it isn't. But to implement a good zero trust environment, you've got to be nailing these things and nailing them properly. You can't just stick together an antivirus installation and say, that's my network endpoint security sorted out. Done. No. You need to take it more seriously than that. Now, exactly what you must do, it's going to vary depending on what technology you're using, what industry you operate in. But basically, zero trust means if it is something that will benefit your security, it's reasonable to do, it's going to get done. And the whole idea is these things must support the whole validate before trusted. Prove I can trust you before you get access to the data. Prove you can be trusted before you get even access to the flippin' internet. You get the idea. Those are the principles of zero trust. And these components, although not revolutionary, are now more important than ever before. But that is all I need to cover with you guys for this. Like I've said, I'm basing this off of things like LPI's Security Essentials. and most importantly, CompTIA Security Plus. And although we didn't get into any nitty-gritty details around cloud security, part of the reason why is because every cloud vendor offers you something unique, something different. So my advice when it comes to getting into the cloud computing properly and getting certified, especially when it comes to cloud security, is to check out the cloud vendors' courses. All the big names in cloud computing have their own courses, quite a lot of them for free actually, if not free, very, very well discounted. And it'll actually serve you better to jump straight into it. So maybe, for instance, you want to get into supporting AWS. Then don't waste your time with a vendor-neutral cloud certification. Jump into AWS when it comes to supporting and securing it. If you want to become a guru at Azure for Microsoft, jump into the Microsoft stuff. The knowledge you'll learn from one of those courses will straight away get you a better chance at a job. And if you want to learn the other vendor at some point in the future, it's just a case of, oh, they call it that. Okay. And then, oh, they already do that for us. I don't need to set that up. Oh, but I need to set that up, and I didn't have to do that with my original vendor. Learn that way. A general security course like this is useful. But if you want to specialize in cloud administration and cloud security, then start specializing in the certifications as well. It's going to be quicker and more time saving and also money saving for you guys. But take that advice as you will. Otherwise though, that was our overview of cloud security and a bit of other stuff like embedded systems and zero trust. Thanks for watching. If you haven't already subscribed, please do so. If you've got any friends, colleagues, family members, or anybody that you think might enjoy this series, don't be afraid to share with them. But otherwise, I will catch you all in the next video.